Today we'll talk in a little bit more details about the Dalton atomic theory to explain the nature of different substances around us. The first postulate in Dalton's atomic theory is that all substances are composed of tiny building blocks that are called atoms. These are invisible. You can see it with your eyes. So you have to have some other way to detect it. And this is what we will discuss in a little bit more details in this lecture. The second postulate is that atoms of any given element are identical. And this postulate here is partially correct. So it is correct that atoms of a given element are identical chemically. However, they differ in mass. The third postulate of the theory is that atoms are indivisible. And this postulate was later proven by experimental measurements to be completely incorrect, because we can actually detect subatomic particles like electrons and protons. We'll see how we were able to detect those. The fourth postulate is that atoms are neither created or destroyed in a chemical reaction, which is called the law of conservation of mass. And this is a correct postulate, at least within chemical reactions. It is possible to destroy atoms in a nuclear reaction, which is not a topic of our course. The last postulate is that when atoms combine or react or interact with each other, they interact in a whole number ratio. So when they form compounds, these compounds have to be in whole number ratios between atoms and each other. Like water is H2O, 2 hydrogen atoms and 1 oxygen atom, not a fraction of any of the species. And as we said, the second postulate has been proven incorrect, because despite the fact that atoms are invisible, you can detect it with your eyes. However, you can do experiments and measurements that will tell you the nature of the atom. So the first experiment in this context was the cathode ray experiment. Like you can see here, this experiment is conducted in an evacuated tube like this. And when you apply a very large electric potential on 2 electrodes, this will cause a beam of particles to be emitted from the cathode to the anode of the cell. And if you allow this beam of particles to pass through, it will move in a straight line, and you can detect it with a plate like this in spot B. If you apply an external electric field perpendicular to the path of the beam, you will find that the beam is actually curving towards the positive electrode, which means these particles have to be negatively charged in order to be attracted towards the positive electrode of the external field. And if you apply magnetic field perpendicular to the path of the beam, you will find that the beam gets attracted to the magnetic field, as you can see by this spot right here, which means it has a magnetic moment on it. So it's a particle that is negatively charged and has magnetic moment. And in another experiment, the mass of this particle was measured and was found to be very, very small. And scientists call this particle electron. And it gives, they give it a symbol E. In another experiment, when you take a radioactive source, which is known to emit positively charged alpha particles, and if you irradiate a gold sample with this positively charged particle, you find that the particles are actually diffracting at different angles. That diffraction is a result to a a collision between the positively charged particles, alpha particles, with something within the atoms of the gold sample. That something is a nucleus, and it has to be positively charged in order to collide or repel the positively charged alpha particles. And that's how we detected a positively charged subatomic particle in the nucleus of any atom, which was called a proton. And the mass of that proton was measured and was found to be a huge mass in comparison to the electron. And of course, as we discussed, it is a positively charged particle. So based on these two experiments, we built the first model to describe the atomic structure as a small solar cell with a massive nucleus that is composed of positively charged protons with this mass right here experimentally measured, along with neutral particles called neutrons with this mass right here. And you can see that the masses of protons and neutrons are almost identical. And just to avoid expressing the number in a huge numerical value like this, we define a new mass unit, that is the atomic mass unit, to equal this value right here. And using this new unit, you can express the mass of each of these particles to be 1.007 AMU for a proton and 1.009 AMU for a neutron. In comparison, an electron is experimentally measured to have that mass right here, which is significantly smaller. It's actually, if you express it in AMU, it's going to be 0.00055 AMU, which means an electron is more or less 100,000 times smaller than a proton. And based on this model, you can see that most of the mass of an atom is actually localized in the nucleus, which occupies a significantly smaller volume of the atom. So the massive nucleus, in comparison to the overall volume of the atom, is actually the same as the comparison between a ball and the field. So it's more or less like 1,000,000 times smaller, which means the atom is actually mostly made out of vacuum. And we said the atom is invisible. You can't detect it. You cannot detect it with your bare eyes, but it is possible to detect atoms using an instrument that is called the scanning electron, the scanning tunneling microscope. And this is an image for an atom. It's actually possible to detect it and manipulate it. So this image here is for a group of xenon atoms on a palladium substrate, and scientists in this case were able to even manipulate the position of these atoms to write an atomic script of IBM, because this was the first time to detect an atom on a lab scale. This instrument is no longer that uncommon. We actually have several of this instrument on campus here. So based on this concept, atoms having the same number of protons will behave identically and will have identical chemical nature, will form an element. So elements, the identity of an element is based on the number of protons. So that number is called the atomic number, and it takes the symbol Z. So it's gonna equal the number of protons in the nucleus of this atom or element. And it has to equal the same number of electrons in order to keep the atom neutral, because in nature, atoms are neutral. The mass of any atom is going to be mainly given by the number of protons plus the number of neutrons. And that sum is called the mass number of the atom with the symbol A. And based on this description, we will use this notation here to symbolize different elements. We will have a symbol that is usually going to be the first one or two letters in the element name, in this case C for carbon, and we will have the atomic number, which is the number of protons, as a subscript, the mass number, which is the sum of protons plus neutrons, and it gives the mass of the atom in AMU units, as a superscript to this, to the left-hand side. And then we will have a superscript to the right-hand side to be the charge on the atom, to indicate whether it's neutral when n equals 0, or positive or negative ion, depending on the neutrality of the atom. Based on this description, we can arrange the different elements depending on the atomic number in an increasing order of atomic numbers in the modern periodic table. So whenever you have different number of protons, that indicates that it's different elements. And again, we arrange these different elements in the order of increasing atomic number to build up the modern periodic table. And we will get a periodic table that looks like this, with an increasing order of the atomic number. And it's going to be made out of vertical columns that are called groups, and horizontal rows that are called periods. And the reason why we call them periods, because it indicates periodicity or repetitiveness in the behavior of the different elements. So we will have groups that will take numbers depending on the position of the group. Group 1A on the most left-hand side of the periodic table, then group 2A, group 3A, and so on. And elements that belong to the same group will have similar chemical behavior. This is why we actually give different groups some specific names to differentiate them from other groups. So group 1 is called the alkali metals. Group 2 is called the alkali earth metals or alkaline metals. And group 7A is called halogens, and group 8 is called noble gases. And you can see that the periodic table is really helpful to have an idea about the trends of chemical properties. Like, all elements on the left-hand side of the periodic table are metals. All elements on the right-hand side are non-metals, and the elements on the border are metalloids or semiconductors. So it actually tells you a lot about what to expect concerning the chemical nature of the element based on the position in the periodic table. From the position of the elements in the periodic table, you can actually decide the atomic number of the element. So, for example,